So, hello everyone, hola a todos los que nos estén viendo. Thank you all for being here. Oh, there. Thank you all for being here. This is the first seminar of the year, and in this opportunity we have Dr. Vladimir. He's a researcher and a professor of astrophysics of the Astronomical Institute of the Czech Academy of Science. He was the director of the Astronomical Institute until last year. He's visiting Argentina and our institute during this week because he's working in collaboration with the astrophysical group here, the astrophysical led by Dr. Romero. His field of research is relativistic astronomy, and some of the topics he studied are the effects of strong gravity in the vicinity of black holes, compact magnetic stars, and dense nuclear stars clusters, among others. And in this opportunity, he's going to talk about the signature of chaos and particle acceleration near magnetized black holes. So we thanks Dr. and Professor Karas for being here and for giving this seminar. So we will start now, and we will have some time at the end of the talk for questions. And some of the people who are watching this transmission might ask some question or comments through YouTube, so we will read them if there are any. Yeah? Great, thank you.
Great. So thank you very much for the introduction, and also for giving the opportunity to talk about our research, which has been done in collaboration with a colleague of mine and previous student, Ondřej Kopáček, at the Astronomical Institute. We are a research institute of the Czech Academy of Sciences, so that is a non-university institution, but we also provide teaching and PhD education to students of the Charles University, mainly the main university in Prague. And with Gustavo Romero we met last year already in Prague when we had a conference, so I apologize because the topic was slightly similar, maybe you heard it already, but now I have many more slides, maybe too many for one talk, so I will try to go relatively fast. If you have questions or if you want to slow down, just tell me, or you can have questions afterwards. And the subject, it worked, but
you also have a stick. You see the stick on the.
No.
It's to change the slides.
It was changing, but it does not anymore.
Y si se lo cambiamos a mano.
Maybe battery died.
¿Funciona o no?
It's working now. So this is a short outline. I would like to go at least through the first 4 points, maybe not the details at the very end of the talk. Initially about a few words about the distinction between regular and chaotic motion, and then its application in astrophysics, and in particular for motion around the black hole. motion of particles in the strong gravitational field of a black hole, but also with the effects of electromagnetic interaction. I will give some equations, equations of motion, from which we derive whether the motion is regular or whether it is chaotic. And then I would like to describe in particular the case of a rotating black hole, which is embedded in magnetic field, so it is magnetized black hole, and the effects of chaotic motion in this situation, and also why we actually do it for astrophysical applications. And then I will focus in this chapter 4 to somewhat not so new, but also not frequently used way of characterizing the chaotic motion using so-called recurrence analysis. That is something which is complementary to Poincare sections. People doing chaos are very familiar with Poincare sections, but maybe I will argue then in case of studying chaos in relativity, this recurrence analysis is more suitable, or it's complementary, because in GR we have always this difficulty or this issue to properly select the frame and coordinates, so some kind of sections may be coordinate dependent, but using recurrence plus it is independent of this complication. So let me say a few words about first about regular and chaotic motion. As you know, the Kepler problem, for example, two-body problem, motion of a planet around Sun is regular. There is no chaos, and this, in other words, means that starting two examples of motion, two planets or two particles with almost same initial conditions means that they will evolve in time close to each other. The trajectories will separate from each other, but in slow linear way. On the other hand, in many situations we find that this is not the case. The trajectories may diverge very quickly, exponentially in time, in fact, and this is what we then call chaotic motion, or this is when chaos sets in. And there is a well-known introduction of the problem by Lorentz in 70s. They show that the separation of two systems, in our case it means two particles, which is a function of time, evolves exponentially with this factor, with this exponential factor, and grows therefore very rapidly. And this chi, this exponent here, is related to what we then call Lyapunov exponent. So as soon as this number is positive, it means that trajectories separate, and you cannot easily actually say what were the initial conditions of the motion. In case of astrophysics, the maybe seminal paper on Isle in 1964 discussed the motion in a simplified manner. They were studying motion of stars in the potential of a galaxy. here you see that it was simplified to the two-dimensional problem, just to the plane, and in that case, the gravitational potential of the galaxy was approximated by this effective potential, where the bar contributes to the nonlinear term, and it appears in that paper they demonstrate that actually some trajectories stay regular, but there are regions of chaotic motion. So in overall, the system does not have enough integrals of motion, and that can be seen in these plots of phase space evolution. So there are 3 examples of trajectories in the phase space. The points, individual points, and these curves, which consist of a large number of points, are actually intersections of the trajectory of a star or a particle moving in this potential with a plane in the phase space. So there are 2 coordinates, like two conjugate coordinates you need to select, make a plane so that it can be visualized, and then the regular motion corresponds to these curves which cross the plane in a curve, but chaotic trajectories are those which jump from point to point and fill the section rather randomly.
So the axes are momentum, position.
And the conjugate position, yes. So you see 3 examples of the trajectory with different energy. As the energy grows, typically the trajectories become more chaotic. So it is this example, but still there are persisting small islands of semi-regular motion. But that was the application to galactic dynamics, to dynamics in the galaxy. This is different application from the solar system. Quite well-known plot of what we call Kirkwood gaps. So the motion of asteroids is characterized on the horizontal axis is the semi-major axis, and on the vertical axis it is the number of asteroids detected with that semi-major axis. And you obviously notice these Kirkwood gaps, which occur when the motion of asteroid is in some ratio, small integer numbers, with respect to disturbing planet, Jupiter in particular. So the gravitational field is the field of the Sun. If there were no disturbation, then it would be just a Kepler problem. The asteroids would be test particles moving on regular Kepler ellipses. But with the disturbance set by Jupiter, for example, or Saturn or Mars, they can actually be set on chaotic trajectories, and that means that those which should occur here, where there is the depression of the number of asteroids, are quickly moved to different, slightly moved to different values of orbital parameters. They repetitively orbit, commensurate with the Jupiter, and therefore they are disturbed from this particular orbit. So these are resonances, of course. And in our case, what we consider is the motion of particles in the field of black hole, and they are disturbed by weak magnetic field. So the particles must be electrically charged so that they feel the electric field. An interesting point here is that if there were no disturbance by this electromagnetic effect, the motion would be regular again. So that is, of course, non-trivial statement, because now we are not in Newtonian approximation, we are not in Newtonian dynamics, but still test particle motion in the gravitational field of a black hole, even a rotating black hole, or even electrically charged black hole, a Newman black hole, remains regular until we switch on the electromagnetic interaction between the black hole or the external fields and the particle. And this is what was discovered in early 1970s. There is rather well-known so-called Carter constant, the constant of motion, which ensures that the motion of particles is regular until they are disturbed. The black hole itself, let us speak about just Kerr rotating black hole, is axially symmetric and stationary. So that means that we automatically are getting two constants of motion. One is related with the stationarity, the energy of the particle remains constant, and the other constant of motion is related to axial symmetry. But it's not obvious that there is a third constant of motion which would ensure regularity of the trajectories. And that also makes the bridge to what I mentioned at the beginning with this Enon Iles work, where they were looking for the third constant of motion in the galactic, in the problem of galactic dynamics, and they found that it does not exist actually in general. So here we consider this kind of system where the black hole is in the center, mass of the donor star. This one is overflowing and forms an accretion disk, but some matter gets out of the accretion disk, forms a corona, and that is very diluted, rarefied environment of charged particles. So they feel electric and magnetic disturbances, and now we are interested in their motion and characteristics of their motion. I think I will not read all this in detail. That just summarizes what I mentioned, that in case of stellar mass accreting black holes, accretion disk develops, corona of charged particles develops, and the motion of those particles is determined by strong gravity, but also electromagnetic forces. Obviously, very close to the black hole, the gravitational attraction grows arbitrarily in a way, but the constants, the characteristic constants of the particles, to znamená, that is the charge and mass, the ratio of charge or specific charge, is such that very weak magnetic fields can disturb the motion quite strongly, very strongly. So as soon as you switch on this electromagnetic interaction, the acceleration, electromagnetic acceleration wins, unless it is really immediate vicinity of the horizon. This is another example of a system where such setup is relevant. That is actually a radio image of the galactic center. So very much different scales compared to stellar mass black holes. It's several parsec scale. Supermassive black hole, Sagittarius A star, is located in the center, and I am showing this image because of these narrow filaments here, which are filaments of matter radiating in radio, apparently tracing the structure of a magnetic field in that region. And their shape is, I would say, linear, long over several parsecs or even tens of parsecs, but very narrow. And that is suggesting that the magnetic field in that region is organized, that it's large-scale magnetic fields to which the black hole is embedded.
And what accelerates its particles? It's non-thermal radiation, right?
It's non-thermal radiation, so I understand that there are discussions about what actually forms these filaments, but presumably they are accelerated particles moving along these magnetic field lines, and this magnetic field should be present probably all over there, but only in the places where you inject some amount of material, they can be traced. And probably they are temporary features which after some time disappear because the particles cool down. So now, what kind of simplifications we take in order to have analytical or semi-analytical description which is tractable for investigation. So a gravitational field is described by Kerr metric, which has an analytical form, and therefore these functions are all known. They can be complicated, but they are given in explicit manner, and they depend on coordinates, of course. So these are spheroidal coordinates, radius and theta latitude, and phi azimuth. And there are two parameters: mass of the black hole and angular momentum or spin. In addition to this, we need some prescription for this magnetic field. And in order to start with the simplest possible explicit example, here we take the prescription for uniform magnetic field. Obviously, that is just one case, but in general situation, in the case of general source of the electromagnetic field, one can make multiple expansion with as an infinite series of terms. And the leading term is the uniform magnetic field. So it is like if you take the expansion of general source and just reduce to the leading term. So this is the electromagnetic four potential components which describe uniform magnetic field on top of the Kerr metric. I should say that it is supposed to be weak magnetic field, in the sense that it does not come back to the metric components. Because in general, in general relativity, also electric and magnetic fields contribute to the metric. So in principle, they should also somehow appear here. But it turns out that when you linearize the G mu, the metric tensor, in electromagnetic terms, in linear approximation, they do not appear, or all contributions are of higher order. So we can stay with the Kerr metric, but still we have this test field which needs to be a solution to the Maxwell equations in a fixed Kerr metric background. And therefore this field is somehow distorted near the black hole. Even if it is vacuum field, it feels the presence of the black hole. And there are two parameters here, Bz and Bx, which are components of the magnetic field along the rotation axis and perpendicular to rotation axis. So one simple example would be, for example, if you put Bz equals 0 and consider just magnetic field aligned with rotation axis, that is probably the simplest situation, just with this Bz here and here, just two terms remain. And that is what is called Wald field, which one can find in many textbooks.
That's what you do Bx equals 0, right?
If you do Bx equals 0,
Bx.
yes. On the other hand, we have this explicit form for arbitrary angle between the uniform magnetic field and the rotation axis. So we can study also the field which is not aligned with the rotation axis.
That's why you don't have a By, or what's...
Well, then it would, By is already kind of not necessary, because you have one axis of the black hole and the other axis of the magnetic field.
Yes.
So
But if it's rotating, right?
if it is, yeah, you can rotate your x and y axis in such a way that y is 0,
okay.
right?
Yeah, I see.
So it's general.
You said the y-axis
in such a way that it is in the plane of these two.
It's a rotating
Yes.
frame.
Yeah.
Right.
Yeah. Exactly.
Now I got it. Thanks.
But you can also set, and I will show it later, Bz equals 0. Yes, Bz equals 0 and Bx non-zero, and then it would be perpendicular to the rotation axis. So that will be, of course, more complicated. It's already seen from the formulas that it's more complicated, and the reason for this complication is the dragging, frame dragging of the magnetic field by black hole. Okay, so this is just a repetition, the gravitational field and the components of the magnetic and electric field, which are given in terms of B vector and E vector, and they are defined as a projections of the F mu nu on the frame of the observer. And this F mu nu is given in terms of electromagnetic force vector. So in this sense we have a complete prescription. Let me show a few examples. So this is the case of the aligned magnetic field, aligned with the rotation axis. And this is the case when there is a small inclination angle with respect to the axis and more inclined fields. So you see that in this case of aligned field, the field lines kind of smoothly pass around the black hole. They are distorted, but not much. while in the case of inclined field it becomes really extremely wild situation.
And so I do not. This is a curved black hole, right?
It's curved black hole and uniform magnetic field.
Yeah, but then why in the first figure the atmosphere is not twisting the magnetic field lines?
Yes, in Boyer-Lindquist coordinates, when you do the solution, which was on these equations, and if you plot it, then this is indeed the result.
It's just an effect of the coordinate.
It is coordinate dependent picture in this way. Because if one would like, for example, to draw how these field lines would look to an orbit, to an orbiting observer or freely falling observer, then this freely falling observer would feel the rotation of the black hole, and therefore also with respect to him, these field lines would be twisted indeed.
And from infinite, you should see the
infinitely twisted. I will have it in a few moments on another picture.
Because always you should have a pointing flux along the
yes.
the
Well,
ZX axis.
But in this case, it is stationary and electrovacuum solution. So I don't think that it's radiating as a pointing flux. As soon as you start ejecting matter, and this matter is somehow moving along the field lines, then it will generate the flux also. But in vacuum,
but for the pointing flux, you only need some perturbation going out in the magnetic field lines.
yeah, but then you need also to connect somehow these currents. So what is in this situation is electrovacuum steady and not changing with time. This is the case of perpendicular field with respect to rotation axis. So here it is spin equals 0, so actually the rotation axis is not defined, but here for maximally rotating you see that the lines are entangled in a complicated way, and it is the best seen if we look on this equatorial plane from top. So these are these three pictures here. Rotation axis is perpendicular to the screen, and the magnetic field lines stay in this plane because they are perpendicular. So for symmetry reasons, they remain in the equatorial plane, and you see that this structure, these layers develop close to the black hole in quite complicated manner, and in particular there are these regions where the magnetic field goes to 0. I can show several more examples. This is another, maybe more general situation where we have a rotating curved black hole, magnetic field which is aligned. So this is what I showed before. And here, when we give a boost to the black hole from left to right. So again, you see that it distorts the field lines, but now this distortion is just due to motion of the black hole, and when it is run away, when it gets some translatory motion. And one more case, the black hole with translatory motion from left to right. but the magnetic field perpendicular to the rotation axis, and the rotation axis is vertical. So you see that these fields are twisted, and that you have regions where magnetic intensity is much larger on one side of the black hole, on the trailing side actually, than on the other side. But still, we are speaking just about vacuum fields, no matter injected so far.
Vladimir, sorry, one question.
Yes.
Do the field lines enter into the black hole?
That's a very good question. So in general, yes, they do. There is a special situation when they don't. If I go back, so it is this situation when you have aligned field and maximally rotating black hole, then there is what is called this Meissner effect, which means that the field lines are flowing along the horizon, but they do not enter inside. But apparently, the Meissner effect is something which comes from the physics of magnets, or superconducting magnets actually, which states that in classical electrodynamics, the magnetic fields do not enter into superconducting material. And that is kind of elementary fact in electrodynamics. So in this sense, it is similar to the Meissner effect, but in reality, it is different on the physical grounds, because we do not have any superconducting matter. There is just a black hole. So it's just geometrical effect. And moreover, it does not hold for different orientations or for lower spin of the black hole. It also does not hold. So it's kind of interesting thing, but maybe not terribly relevant for astrophysical applications, because you always have some matter which will be dragging these field lines into the black hole. Okay, this may be actually interesting visualization of the magnetic line structure. You see that is the field lines are shown by these lines flowing along the horizon, and the associated electric component is plotted by color. So this plot wants to show you two different things. One is that close to the horizon we develop this changing structure of layers of the magnetic field. And the other one is that there is also an electric component which is generated by gravitomagnetic interaction between the magnetic field and gravity of the black hole. I can show it here in detail. So the black hole horizon is here. That is just a small detail of the system. And if you look to the direction of the field lines indicated by those white arrows, you actually see that there is a magnetic null point here, which means that magnetic field goes to zero. And the argument is that as soon as some amount of matter is injected in the system, then these magnetic field lines start reconnecting in this place, because then there will be a conducting medium, and the field lines will be able to reconnect.
What's causing the layer structure?
It's interaction between the there is this rotating black hole which is twisting the magnetic field lines, and that is all actually. Okay. So the solution or equations which you are supposed to solve are just Maxwell equations.
Yeah. Okay, so the rotation along with the gravity pull
Yes.
and compresses the lines and creates layers.
Yes, creates these layers.
And then in these layers, in between the layers, you create nulls. Recollect?
Yes, yes, exactly. You
Right.
cannot null points, and that is a steady state solution, the vacuum solution of these Maxwell equations. So it will not be changing in time until you put some matter in. This is for complete this structure of electric field lines. So similar set of pictures, but for electric component, which is induced again by the rotation of the black hole. I just remind you that we start with the magnetic field, which is uniform, so there is no electric field at the beginning, but then there is this rotating black hole, and the gravitomagnetic interaction induces electric field. And there are 3 examples depending on how the black hole is moving. But it's interesting already in this left case, which is the simplest one. So that is just standing black hole rotating and the uniform Wald field, Wald magnetic field, and these are corresponding electric field lines. So you see that these electric field lines are radial at large distance, but they are going inside here and outside along the equatorial plane.
And they do not enter into the black hole.
In the case of maximally rotating black hole, they don't enter.
They don't enter.
But only in this case. But if you would like to consider analogy with classical electrodynamics and have a rotating sphere instead of black hole, like neutron star, for example, then this electric component, which would be induced, is a quadruple term, quadruple electric field. So you see that in the case of black hole, the structure is completely different, and that is because it is a rotating black hole and it's gravitomagnetic interaction. And finally, this picture of both. Blue are magnetic field lines, red are electric field lines. So that is consistent solution of both together. And z equals 0 is equatorial plane. So if you look to the shape of magnetic field lines here, you see that there is this magnetic null point because they are flowing away from this particular point here. You can show it maybe better on this picture again. Z equals 0 is the section of the equatorial plane, and the magnetic field lines are creating this magnetic null point. But now the argument is that the red lines, which are electric lines, are going through the magnetic null point. So if you inject a charged particle into that region, there will be no Lorentz force on that particle because the magnetic field is 0, but it will feel this electric component, and so it's a very convenient situation for acceleration of the particle, right? No magnetic field, just electric component. Maybe skip this. That is another type of picture of magnetic field lines and the magnetic null point here. And the summary of the structure of those electromagnetic fields is here. So there were already several questions in this direction. This Meissner effect, this expulsion out of the horizon, is indeed dependent on the system and is not generally valid. New electric neutral points form, and in these magnetic null points, the electric component can accelerate the particles. And finally, in the conclusion, I can show this characteristic of motion of particles in this system. So what we now want to solve is the equations of this particle motion, which of course in a classical textbook is usually written in terms of geodesic motion, but with the source term on the right side, so it's not geodesic motion, but it's accelerated. But in our problem, it's more convenient to use a Hamiltonian formulation, and this is the Hamiltonian for the motion of particles. So there are generalized momenta, charge of the particle, four potential components, and the metric tensor, and this forms Hamiltonian, and the equations of this particle motion is then written in this form. We can also find effective potential for this type of motion. So again, this analogy to this anon-aisle effective potential, which I had in the beginning. And this, in our case now, this effective potential is again the function of coordinates r and theta, spin of the black hole, charge of the black hole, spin of the charge of the particle, and angular momentum of the particle. And this is the explicit form for the effective potential, which one can derive. Of course, we don't have time to go into details of this form, but I just tell you that this effective potential depends on parameters which are basically all known. So they are coordinates, metric tensor, components, and charges. And when you make a plot of these effective potential for different values of parameters or different energy of particles, you can get this kind of structures. So the black hole is in the center, and the curves show you the equipotentials when you put matter into this system. It can remain stable when it is within the closed equipotential lobe. So if you are doing Yaroshinsky, Abramovich thick accretion disks, then they do not consider this electromagnetic interaction.
No,
right?
they don't do not.
Yeah, they don't. And in that case, these two lobes here merge in the equatorial plane, and you have just one accretion disk or accretion torus. But with the effect of this uniform magnetic field now, these lobes split, so they actually form two stable configurations. One is above the equatorial plane here, the other one is below the equatorial plane, and they are held by the Lorentz force, basically. The particles are orbiting or the fluid is orbiting.
So you would have
Above
like
and
two
below.
fluids like this,
Yeah, so we have like two
like two donuts, one.
tori. Yeah. But then when you increase the pressure or energy of particles, then this is the next equipotential surface, and they fill this region. So particles actually can move from up to bottom. And then in this situation, for example, you see there are not closed surfaces. So this means that the particles can escape up or down along the axis. So that is some kind of analogy to the
Wind.
jet motion or wind, up or
Yes.
up or down. But the motion in these lobes is not regular anymore, and one could show it either by plotting those Poincare sections, like at the beginning, the Anon islet, but it's a bit more tricky now, because again, as there was already the question in this direction, it will depend on what coordinates you choose for plotting this section. So it's not obvious how make the selection which will be independent of which will be covariant, independent of the frame. But what is invariant is the fact that when you start two trajectories close to each other, they are separating exponentially. And this is nicely formalized in terms of recurrences or so-called recurrence plots in the phase space. So let me finish just by showing this structure. We are introduced, so there is a trajectory x as a function of time, and we measure the distance between the position of a particle at a certain time, I, and a later time after this particle moves away. And we can define the matrix with two indices, where we plot the distance between the position of the particle at one time and in the other time. Let me skip this. Maybe this is clear from the picture. So this is the trajectory of a particle in phase space. We make a tube with some elementary epsilon cross section along this trajectory, and we look how long it takes until the particle comes again inside the tube, meaning close to the original position. And we know if the system is closed, that sooner or later it must come in the phase space, whatever small distance you select, the trajectory comes very close again. So we make, or we plot black dot when the particle is close to its original position, and otherwise we plot a white dot. This is the example of this matrices.
Sorry, I have lost here. So you said, if you can you
Yes.
go back? So you say that if epsilon is small enough, you can say that the second time the particle visits that region,
Yes.
it will have the same trajectory principle, right? Is that what you said, or
This is one trajectory. I mean,
Yeah.
at two different times.
And then,
At two different times, and if you wait long enough, the particle will come arbitrarily close to the original position. Yeah, that is kind of general theorem. But there is a difference whether these trajectories, whether the trajectories separate exponentially or linearly
But
with
you're
time.
to say if it's chaotic or not.
Yes, exactly. And it is shown on these plots what difference we can expect. So on the left side, that is a regular system, so the motion of particle in the regular system. On both axes we have time, so it's this R matrix R at time I and J. And there is always this line of identity. The particle at the same time makes a black dot here. But then because it is a regular system and the particle makes regular orbits, you can find also the same particle here, repeats regularly in time, which is trivial. But then when the chaos sets in, then neighboring particles are separating exponentially. Of course, we are integrating this system numerically, so even if you speak about one trajectory, then with numerical, whatever small error after some time in the chaotic system, you get this signature, and the effect of that is that these regular lines decay into this kind of structures. So this is typical recurrence plot for chaotic system.
And it's a numerical effect.
Well, this is
or the chaotic system.
chaotic system with numerical accuracy, so to say. That there is this parameter epsilon which you need to somehow tune.
Okay, let's see.
But on the other hand, this is, you see, this is a stochastic system in the sense that the dots are given stochastically arbitrarily, and it is still different from the chaotic system, right? It is just noise, this one, while this is a chaotic system. So, and there is a literature about recurrence plots. So what we are actually doing is investigating this type of motion near black hole with different parameters and finding where we have the regions of the chaotic motions setting in. So I think I am speaking now more than 1 hour, so it's probably time to stop at this point. But of course we'll be happy to, there were already questions, but I will be happy to answer more or discuss later, because I think it's an interesting possibility to having, first of all, this acceleration from the magnetic null points, which are developing just for geometrical reasons. That is something which is not used in classical discussions of magnetic reconnections, where these magnetic null points develop just because of motion of plasma. So that is one thing, and the other thing is this effect of chaoticness or transition to chaos, because in non-magnetized black holes the motion is regular. So the question now happens, the question arises when and how this motion stops to be regular and when it starts to be chaotic. my example was about the magnetized black hole, but similar question emerges, for example, when you talk about the motion near neutron stars, when the gravitational field is not parametric. As soon as the gravitational field is not parametric, then this miracle of Carter constant disappears, and you expect that chaos can be again.
One question, but if you increase the intensity of the magnetic field at some point, I think all chaotic behavior should be destroyed because particles will be compelled to follow just the magnetic field line.
That is.
So, where in all your analysis is the relation between the energy density in the magnetic field to the energy density of the gas, of these particles, whatever? Checking the.
I think I don't have the plot here, but the other extreme which you mentioned is maybe what is known as the guiding center approximation, and that is the other limit, that you just plot the motion of particles when you disregard the Vladimir rotation along the field lines. You take just the guiding center, right? And one can investigate the shape of these trajectories, of the guiding center trajectories. I think that was started in old works by Damour and Ruffini already in the 70s. And then you find also that these guiding center trajectories have the direction of the jet-like motion, so particles will move up. But so that is the limit when you stop considering this Vladimir rotation.
But no chaos at all. Case.
Then there should be no chaos, I believe.
Okay. Is there any other questions? Marcelo, ¿en YouTube tenemos alguna pregunta?
En YouTube, ¿hay alguna pregunta?
No.
Okay. I have a question.
Okay.
Do you know of any works where they have studied the configuration of the magnetic field, but in wormholes space-times instead of a black hole?
I am not sure whether there is such discussion in this Orange Book proceedings, but Stuchlik was doing this considerations.
Okay.
And indeed, it's there is the whole methodology or formalism to study this kind of problem with different gravitational fields.
Okay.
Like wormholes also,
Okay.
or even baked singularities.
Okay, because when you study the shape of these magnetic fields, you said that you assume that you have a parametric, and then you solve Maxwell equations. That maybe you will solve them numerically, and that will give you, depending on the reference system that you are adopting, the shape of the magnetic. But basically, that will be the procedure.
Yes, but so because we disregard the effect of magnetic field on the metric, you can use basically the same procedure for any other source of the gravitational field. You take the gravitational field of the wormhole, and you can solve the magnetic or Einstein Maxwell equations of the magnetic field in that field. But the beauty of doing it for the classical black hole parametric is that can be done really analytically without encountering singularities, which probably with wormholes or with naked.
But singularities in which sense? Because wormholes have no singularities. You mean in the solutions that you are getting?
Unless you have the singularity in the system, then it will become difficulty in interpretation. But you can proceed the same way.
Okay.
This is what I wanted to say.
Okay, thanks. Okay.
Okay.
Okay,
Thank you, Vladimir.